What's up, everybody? It's Dan from sagemathtutoring.com here with some pre-calculus stuff. All right, so determine whether each function is continuous at the given x value. That's mission one. Justify using the continuity test. Okay, that's mission two. And then finally, mission three is if it's discontinuous, identify the type of discontinuity. So the criteria for whether or not um, a function is continuous is as follows. So you know a function is continuous at x equals a if these three conditions are met. The function is defined at that point. In other words, if you plug in the x value of that point, you actually don't run into a problem. We're defined at that point. It doesn't result in like a zero in the denominator or something. Okay. Um, Number two, the limit exists as x approaches that point. So in other words, the left-hand limit and the right-hand limit both have to match each other. We're going to be using a table of values for this part. We're going to approach that particular x value from the left, and we're going to be approaching that particular x value from the right, and we're going to see if they match. And then finally, if it's the case that the function value equals the limit, well, then we know for sure that the um, function is continuous at that particular point. Okay. Now, what does this mean? The function value. Well, the function value is the y coordinate that you got after plugging in x up here. And the limit is the y value that both the left hand and the right hand are approaching. Now, that could sound kind of heavy and weird, but the good news is I did break it down into something somewhat resembling a step-by-step process where really, for these problems, you're just going to plug in the x value to see if the function exists at that value. And then I broke it up into two columns. If the function exists, that is this column. And if the function doesn't exist, that's this column. All right. Now we're just going to kind of use this as a tool to kind of work through these problems now. Now let's see. Um, Checking this one out right here. X plus 2, x squared minus x minus 6, and we're investigating whether or not it's continuous over x equals 1 and whether or not it's continuous over x equals -2. Now, this is a table of values that would help us investigate what's going on with x equals 1. And the reason I know that is because really there should be like a 1 right there. There is no table of values pertaining to x equals -2. And to me, that might be a typo on this worksheet. I kind of feel like there really should be. So I'm going to create one literally right now where the table of values is going to somewhat resemble this one. It's cut down the middle. You have a column here, you have a column here. The whole thing is split into two rows. Um, and you could think of -2, which once again is this value right here represented there. So it makes sense that since it's negative, if you go to the left a little bit, I think you understand that that's going to be -2 point, let's call that triple zero one. This would be -2 point double zero one. This is going to be -2 point single zero one. So in a sense, I'm kind of modeling that off of this, what the teacher had provided over here. This was a positive one, so it kind of looks like that over here. This is a -2, so it's going to mirror that on that side. Over here, we're looking at negatives 1.999, -1.999, and -1.999, kind of modeling that of these. All right. So anyway, that's kind of like there waiting for us, which is nice. Regardless, let's begin the process now of investigating what's going on with x equals 1. Okay. So when we go about this, well, as I said in the thing, plug in the x value to see if the function exists at that particular x value. Well, let's take a look at the situation. Of course, we could plug in 1 right now. Um, Not a bad idea. You know what? Let's go ahead and do that. Let's just plug in 1 right now. Now, we could factor the bottom, but I'm seeing, I don't know if it really matters if we factor that. So we would end up with 3 over -6, aka -1/2, aka -0.5. Okay, so that is the sort of special y value that we got. So we discovered that the function does indeed exist. So we're going to note the y value that we got. Well, the y value that we just got is -0.5. So we're just going to kind of leave that there. Now, according to this column, if the table values match each other and the y value, then the function's continuous. Okay, well, let's just see if the table values match each other. We're going to fill in these and we're going to fill in these, okay, using a calculator. Now, I'm going to use a calculator right now, and I'm going to fill in all of these. This is just a matter of plugging in zero point 0.9 in for x, seeing what y value you get, plugging in 0.99 in for x, seeing what y value you got, 0.999, seeing what y value you get, and I'm just going to do that right now. So when I investigate the x value of zero point 0.9, I end up with negative 0.476. When I investigate the next one, it's negative 0.498. And then when I do the next one, it's -4, negative, pardon me, negative 0.499. So it's clearly getting very close to negative zero point 0.5, but let's see if these end up matching. We really want to look, to be honest, at these two to make sure that they are really close to each other. Um, Although I am going to fill out everything because it does appear that the uh, teacher wants that, right? So we have 1.0001 that I have to plug in. Let's see. That would give us negative 0.5000. If we were to then investigate the next one, that's negative 0.5002. And if we were to investigate the next one, that would be negative 0.503. So as you can see, the y values from the right are getting closer and closer and closer to negative zero point 0.5. So the bottom line is these two match. And that's what I mean by this. Do the table values match each other in the middle? Okay. Well, they do. And they match the purple y value. And they match the y value that we got before when we plugged one into the function. So the function is indeed continuous. And I feel like we just justified it using the continuity test. So we just found out that yes, we're continuous at x equals 1. So now, of course, we have to investigate, are we continuous at x equals -2, right? So let's take a look at that. So, the first thing we should really do then is, um, what we had said before, which is to plug in the x value to see if the function exists at that x value. So we're going to plug in -2. So let's find out what f of -2 is. Now, again, the function's right here. So that's going to be -2 plus 2. That's going to be -2 squared minus -2 minus 6. And that is going to be a 0 on the top. We would have 4 plus 2 minus 6, and that's going to be a 0 on the bottom. So it's really the presence of this green 0 on the bottom. That is the problem, where we now know that it's undefined. Okay, when you plug in the x value of -2, the function itself is undefined. So that puts us in this column. If the function doesn't exist at that x value, we're in this column. Now, as you can see, we still want to see if the table values match each other at some, match each other, let's just say, right? So I'm going to go ahead and investigate over here now. Um, so let's see. Let's investigate what happens in my calculator when I plug the x value of -2.01 into this, right? We're going to find out. Well, that is going to be, I'll just do it right now. That is going to be negative 2.01, negative 0.1996. Now, if we do the next one, that's going to be negative 0.1999. And then if we do the next one, that's going to be um, negative 0.19999. Okay. And then if we do this next one here, that's going to be negative 0.2 triple zero. If we do the next one, that's going to be negative 0.2 double zero, and then we got a 4. And then if we do the next one, that's going to be negative 0.204. So as you can see, this right here seems to be approaching negative zero point 0.2 here, and this seems to be approaching negative zero point 0.2 also. Now, this is already negative zero point 0.2, but to be clear, there actually was a 4 sort of at the tail end of this, so it wasn't exactly negative zero point 0.2, but probably it looks like it's trying to get to negative zero point 0.2 here. So what we've done is we've established that these match. And that's very important information. Let's look at what my table says. If the table values match each other at some finite number, like negative zero point 0.2, that's some normal finite number. It's not the nicest number. It's a decimal. It's negative. Nobody likes that. But it's not infinity. It's negative zero point 0.2. So if the table values match each other at some finite number, then it's a removable discontinuity, and that means that it's a whole. Okay, so I hope that makes sense. As you can see, the table is amazing that I made. I would say this table is amazing too, but this one in particular. By the way, feel free to screenshot that, steal that if you want right now. Press pause, screenshot it, steal it, whatever you got to do. Boom. All right, looking at this. Now, of course, they can't help themselves. They're going to give us a piecewise function. Of course, they're going to give us this that's really far away to make it super annoying. Um, and let's see what's going on here. We have this at our disposal if we need it. Um, okay, so this is for all the values greater than 2. That's what this row is all about. This is all the values less than or equal to 2. So that's what this row is all about. And I would say they're being very kind to us because they actually gave us the tables filled out, okay, for us with this one. And it is the case that they want us to investigate what's going on with, around x equals 2. Now, as you can see here, we're leading up to x equals 2. Um, you know, from here to there, we're getting closer and closer. And from um, this position all the way to this position, this puts us really close to x equals 2. Okay. Now, again, they did the table for us. Okay. Now, as a preview, since the tables look a little different, let's be very clear. We would be interested in whether or not these y values match each other, and they don't. So that's already a preview of what's to come. But let's remind ourselves of the process using my table, right? So, according to my suggested protocol, plug the x value plug in the x value to see if the function exists at that x value. Well, that is the first thing probably to do. We can plug 2 in. Now, we shouldn't plug it in to this function up here because this function only corresponds with x values greater than 2. We should plug it into this function because this function corresponds with x values less than or equal to 2. So when you plug 2 into this, well, you're going to get a y value of 2 minus 1, which is 1, right? So there's your purple y value, right? We just plugged 2 into this one, and we ended up getting that purple 1. So the function does indeed exist at that x value of 2, and it yields a purple y value of 1. Okay, so now we go through the motions, right, to see what's going on, because of course we are in this column. So if the table values match each other, okay, let's pause there. We already discovered they do not match each other. This one's going to about 1. This y value is approximately 1, and this y value is approximately 5, right? So we need to look down here. If the table values don't match, then it's a jump discontinuity, which is common in piecewise functions. Well, this is indeed a piecewise function. This y value does not match this y value. So therefore, yes, jump discontinuity. Okay. Um, that's the last problem of its kind. I want to just go over the rest of this. If you plug in the x value and it finds out that the function doesn't exist, that lands you in this column. The function doesn't exist at that x value. If the table values match each other at some finite number, then it's a removable discontinuity. We already did that. If the table values shoot up or down, it's an infinite discontinuity. In other words, if this y value is shooting up into the stratosphere, and this y value is shooting down into the stratosphere or up into the stratosphere, okay? Like getting really large, right? Or really small, then it's an infinite discontinuity. That means that there's an asymptote there. Now, even when we're in this column, let's backtrack. The function doesn't exist at that x value. We had plugged it in. And then if the table values don't match, but approach some finite number, then it's a jump discontinuity common in piecewise functions. Okay. So that is similar to this. So even if the function doesn't exist at that value, at that x value, um, you need to investigate, do the table values um, misalign, right, such that they don't match? If so, if it's the case they approach some finite number, the y coordinates approach some finite number, similar to this, by the way, um, it's a jump discontinuity. Okay? That's common in piecewise functions. So even that can happen even if the function doesn't exist at that particular x value. That just simply describes a scenario where maybe one part of the piecewise function is here and another part of the piecewise function is there. And it's the case that there's certainly a jump discontinuity, but there's also a hole here and a hole here. So the function doesn't exist at this particular x value. That's what this is describing. Hopefully that makes sense. All right, looking at this one, determine between which consecutive integers the real zeros are located on the given interval between 3 and 8. Okay, this would be, like, intermediate value theorem type of situation. So I don't know if I want to dive into the intermediate value theorem necessarily, but I want to get into just the logic behind everything we do here. The bottom line is they're inviting you to fill out these y values, right? These are x values here. You're starting with the x value of 3, that's sort of at the beginning of the interval. And then you do these consecutive integers, 3, 4, 6, 7. And then next thing you know, you have 8, which is the end of the interval. Okay, so it really does seem like these are x values, and this is going to be your g of x values, also known as y. You can think of it as y values, right? So I'm going to use the calculator to plug in each of these. Um, well, do I need to? Oh, yeah, I should. Yeah, I'm gonna use the calculator to plug in each of these into this. I'm realizing there's this -6 here, sort of at the tail end, that we need to not forget about that. And let's just fill this in right now. So when I plug in 3 into my calculator, I get -4.26. 2.8-ish. When I plug in 4, I get negative 2.8377. When I plug in 5, I get negative 1.6411-ish. When I plug in 6, I get negative 0.522. We're getting closer to 0, I'm noticing. When I plug in 7, we're getting this. Okay. And when I plug in 8, I get 1.6157-ish. Okay. So, what does this mean? First of all, what is a real zero? A real zero is anywhere where you have a curve, like some kind of a weird graph, right? And it's the x values where it crosses the x-axis, aka the x-intercepts. We also call these the zeros. Now, let's make an interesting mental note. If you have a negative y value, if you have a negative y coordinate corresponding with a negative y value, you have a point with a negative y coordinate down here, and then all of a sudden you have a point with a positive y coordinate. So that's positive, right? That's negative. Well, in order to switch from a positive y coordinate, from a negative y coordinate to a positive y coordinate, doesn't it make sense that we had to have passed through the x-axis? So that means that there had to have been an x-intercept between the purple point and the yellow point. So my student watching, sure you get that. That's the principle that we're using, okay? They want to know, where are the zeros? Well, it's very easy. We just have to figure out, where do the y coordinates switch from negative to positive, or vice versa? Well, the y coordinates are all negative here, but then all of a sudden, boom, it switches to positive. So we know that between this point and that point, like this is a point, 6 comma negative 0.522. This is another point, 7 comma 0.5574. Between those 2 points, we know that there's a zero. There's a real zero. Okay? And they want to know between which consecutive integers. Well, between 6 and 7. Those are the 2 consecutive integers where we know there's a real zero. Okay? So what would the answer be? The answer would be, uh, you could always use the teacher's words, right? Um, the real zeros, the real zeros are between the consecutive integers of 6 and 7. Okay? That's that. Find the average rate of change in the given interval. Well, this is nothing more than the slope formula. The slope formula, do you remember back in the day learning x1, y1? You have another point called x2, y2. And then you have to find the slope between the points. Well, the slope is m equals y2 minus y1 all over x2 minus x1. So let's draw our attention to these. That's the x coordinate minus the x coordinate, right? That's the slope formula. Now, believe it or not, we're kind of going to use that. Um, let's say the graph of this looks like gobbledygook like that, okay? But we're only really interested in the uh, x1 and x2 x values. So let's say at -1, we're here. And let's say at -5, we're here, right? Isn't that the interval that we're kind of looking at between -5 and -1? What they want to know is, if you were to draw a line between these points, a perfectly straight line, what would the slope of that line be? That's essentially what we're doing, right? but you need the y coordinate of this point. Like if you're going to do the slope formula, in a sense, you could say you need the y coordinate here. So it would be like -5 comma y1, right? This right here would be like -1 comma y2, right? But how would you get the y coordinate? Well, you could plug -5 into the function and then it would produce your y coordinate. If you want the y coordinate for this point, you would plug -1 into the function and it would produce your y coordinate, okay? Now, I'll just tell you that the average rate of change, um, a lot of teachers call it AROC, okay, average rate of change. And a lot of teachers actually would call this interval, um, they would call this A and this B, okay? So we're going from A to B. And many teachers and textbooks would say that the formula is exactly like the slope formula. It's just that it's going to be these are sort of x values, so it's going to be b minus a, and then it's going to be f of b minus f of a. Okay. Now that could be super confusing, but let's just take a deep breath and realize that this holds our answer. All we have to do is fill in the proper characters here. And then we have the answer because that's what they want. They want the average rate of change. Well, we already know that A is -5. I made it clear right here. We know that B is -1. Well, that's a beautiful thing. That takes care of this. Well, what is f of A? Well, that's going to be f of -5. F of -5 is what happens when you plug -5 into this, right? It's going to be -5 to the 5, right? Plus 2 times -5 to the 4, plus 3 times -5, minus 12. And what is f of b? Well, f of b would be f of -1. What is f of -1? It would be the exact same structure, except we're plugging in -1. So we have that. Now, obviously, let's use our calculator because who wants to do this? So when you plug in -5, you're going to get -1902. And when you plug in -1, you're going to get -14. Okay. So big difference, right? Definitely a big difference. So let's see, x to the fifth plus 2x to the fourth plus 3x minus 12. Yeah, it looks like I did it right. So now that was annoying, right? Maybe. But now we have our f of a, and now we have our f of b. We also have our a, and we have our b. So all we need to do is fill this out, right? So A rock equals f of b, that's -14, minus f of a, that's -1902, all over b minus a, that's -1 minus -5. And that's going to be, at the end of the day, 472. Okay, that's the average rate of change. So it kind of took me long to say that, okay? But it doesn't have to take long to do it yourself. How do you do it quickly? Write this formula down, put it in front of you. This tells you the cast of characters you need. Find out what your A is, write it down. Find out what your B is, write it down. Find out what your F of A is, write it down. Find out what your F of B is, write it down. Plug it all into the formula, and there you go. All right, little bit of calculator action, but that's all. Okay, graph the function on your graphing calculator. Sketch the graph, approximate the nearest hundredth, the relative or absolute extrema. Yeah. Well, this is very much having to do with the TI-84. So let me get that going. Okay, so I had gone to the y equals sort of in the top left kind of area there and put in the function. Can't hurt to graph it, so I'm going to hit the graph button. And here we go. We have this function here. Now, for my student watching, you could always use the zoom feature. Like if you click on that, you can zoom in, you can zoom out. You can adjust the window settings to find out exactly like where you want to look at on the graph. Now they had asked for relative extrema, relative min, relative max. Now they had also mentioned absolute extrema. Now this goes up forever to the left. As x goes to the left forever, this thing goes up forever. So there's really no max to speak of because it's sort of a moving target. There's no absolute max. Um, and as x goes to the right forever, this graph goes down forever. So we could say that there's no real absolute min to speak of because that would be a moving target as well. It's like infinity, it's going down forever. We do see that there's relative min and relative max. There's certainly a relative min associated with this, and there's a relative max associated with this. So the question is how do you use a TI-84 to do that? Now, I'm using a TI-84 app, which might be a little bit different than a regular TI-84, but it's very similar. What I could say is you're going to want to go to second and then calc, and it's already saying, do you want to find a minimum? Well, yes, let's go to number three, which is a minimum. I'm going to press enter. It's now asking for the left bound. So for my student watching, you're probably going to have something like that. It might be some little cursor that's like on the curve or whatever, but for my app, it gives me this weird line. But I'm going to go slightly to the left of the min that I'm interested in, and I'm going to hit enter. Now it's asking me for the right bound. So I'm going to go slightly to the right of the min that I'm interested in, and I'm going to hit enter. And then it gives it to me. It is actually that negative 1.08321 thing. Okay, now I can zoom in a little bit. We're clearly looking at this. I'm actually going to hit that with my finger, and it makes it very clear that those are the coordinates of that point. Now, with regards to relative min, it's that y coordinate that we're interested in. So it's negative 1.08-ish. Okay, negative 1.08321. Now, of course, we also want this relative max right here. It's going to be a very similar process. So I'm going to say second calc. We're going to go down to maximum. We're going to hit enter. It's asking for a left bound. So here's a nice left bound. I'm pressing enter. It's asking for a right bound. Let's go to the right. I'm pressing enter. And what do you know? It's telling me that that y coordinate is at 2.12-ish. So I'm going to zoom in and I'll just hit that right there. And it's 2.12136, right? So that is that. Now I'm just freely zooming in with my fingers on this app. You're not going to be able to do that on the TI-84. It's going to be a bit more clunky on the TI-84, but it's nothing you can't handle. So anyway, that's how that goes. Okay, so hopefully that makes sense. I am noting that the teacher specifically asked to approximate to the nearest hundredth, and these are indeed approximations. So the nearest hundredth is that position, right? It's that position. So we really are looking at negative 1.08 here, and we're looking at 2.12. So these are the answers you will want for problem number five. Okay, use the graph of each function to estimate the interval on which the function is increasing, decreasing, or constant. Okay, this is gonna be freaking awesome. Oh my God, this can be so easy compared to what we've been doing. So let's be very clear. This thing is decreasing as it goes down from left to right. So I'm gonna do a little red action to denote where it's decreasing. Where's this thing going down from left to right? In other words, if I was a skateboarder and I was going uh, from left to right, which is like in that direction, where on the graph would I be plummeting downward? Well, I'd be plummeting downward in this section, wouldn't I? I'd be going all the way down. I'd also be going down in this section if I was skateboarding here. And that's it. Where would I be going uphill as a skateboarder? Well, I'd be going uphill here, and I'd be going uphill here. Now, that looks like it's only decreasing in the red and increasing in the right. There's no constant. Constant would mean that it's going flat straight across. So let's talk about decreasing. It's decreasing on the interval. Well, this arrow means it's going up forever, but it's also going to the left forever. So it's certainly decreasing from negative infinity all the way up to whatever that is. That looks like it's a -3, right? And when we're talking about the intervals, we're talking about the x values. Over which x values is this thing decreasing? Well, it starts at negative infinity, and then it keeps decreasing, 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 decreasing until you get up to -3. So -3. Now, at -3, it's neither increasing nor decreasing. So we put a parentheses there. You always put parentheses next to infinity symbols. So that's the first red part. Now, the second red part's right here, but as my student watching probably knows, I got to do the union symbol. So over here, we're going to go from, I don't know, -1.9, right? -1.9. I'm happy with that. -1.9 all the way to zero point 0.5. Let's go for it. Zero point 0.5. And that's going to be also parentheses, parentheses, because at -1.9, at this x value, it's neither increasing nor decreasing. Okay. Now, these values that we've chosen are going to be important for the next part because as we talk about where it's increasing, we need to kind of match those. It's increasing from here to there. Well, we already called this one -3, and we already called this point -1.9. So it's increasing from -3 to -1.9. Now that's going to be important. Your teacher is going to want to see that you know that that -3 needs to correspond with this, that -1.9 needs to correspond with that. So we have a union, then it's increasing from, let's not make this up on the fly. We called that zero point 0.5 before, so it's increasing from 0.5 to infinity. So we have parentheses and then we're done, and then we're getting an A on the quiz. And then we have this one. Where is it increasing? Certainly increasing here. There's a skateboarder going uphill, right? Going uphill. As we push him from left to right, he's going up. Right? Where else is he going up? He's going up here. Where's this thing going down? Well, it's going down here. Where's it going down? It's going down here forever, by the way. Where is it constant? Let's use purple for that. It's constant here. So let's focus on increasing first. It doesn't matter what you focus on. So it's increasing. Looks like it from negative infinity all the way up until approximately -1, 2. That looks like -2, right? So negative infinity to -2. By now we know parentheses, union. What's this? All right, that's going to be 2. Let's make our life easier. 2, 2. All right, we're definitely calling that 4. We're making our life easier. 2 to 4. So over the interval from 2 to 4, it's increasing. Hopefully my student watching understands. Where's this decreasing? Well, that's the red, isn't it? Decreasing from 3 to negative, oh, pardon me, decreasing from -2 to -1, right? And by the way, we stole that -2 from here, didn't we? So we have -2 to -1. Where's the -1? The -1 is right here. So it's decreasing from -2 to -1. Union symbol. Where else is it decreasing? Well, it starts at 4. We could steal it from here. It starts at 4 and then it goes down as we go to the right forever. So that is 4 to infinity. Okay. Where is it constant? It's constant between this value and this value. But once again, we called that -1 before, so we're still going to call it -1 all the way until 2, which we used earlier. So from -1 to 2, boom, that's how you do that one. So let's zoom out. Once again, use the graph of each function to estimate the interval on which the function is increasing, decreasing, or constant. And we did that, and we used interval notation. All right. Now, for my student watching, please be very organized about how you're communicating. A little D or DEC for decreasing, a little I for or INC for increasing with a little colon, right? Get the big picture in place. Understand this is your checklist. Write that down first and then kind of go from there. Okay, problem number 7. Model rockets launched from the roof of the building, flight path modeled by blah blah blah, where h is the height of the rocket above the ground and meters and t is the time after the launch stage. What's the maximum height? All right, they probably want you to use your calculator again. The bottom line is we could most definitely graph this on the TI-84. Now, let me go ahead and do that. Okay, clearing this one here, we're looking at -5. Now, it said t squared, but we're going to call it x squared, -5x squared plus 30x plus 10. Let's go ahead and graph it. Now, if you were to zoom out, a lot, it would do that, right? And if you were to zoom out again, let's say we choose to zoom out using the features. But anyway, you get the idea. You can keep zooming out, but the bottom line is the maximum height is here. Now, we already talked about how to find the maximum height. Now, by the way, let's be very clear. The y-axis represents the height of the object, and the x-axis represents time passing by. So it looks like over here at the y-intercept, that's the height from which the object launched. Maybe I guess it started at 10, right? It launched from 10 feet up or 10 units up, and then it went, as time went by, it went up, 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 and then it went, um, all the way to the ground, and this sort of ground floor here, that represents the ground level, when it hits the x-axis. So if we were to use the TI-84 sort of maximum thing, of course, it's second calc. We are looking for a maximum. I'm just going to hit number 4 right now. It's asking me for the left bound. I'm going to go to the left. I'm going to hit enter. It's asking me for the right bound. I'm going to the right. I'm hitting enter. And then lo and behold, there you go. It's telling you it's 55. Okay. So it went up 55 feet, and that happened at 3 seconds. All right, so we can see definitely the maximum height is 55. Now, it wouldn't be unrealistic if the teacher also asked um, not only for the height, the maximum height, which is 55 all the way up there, right? It's the y coordinate up there, right? Y coordinate right here. But the teacher, of course, could ask, well, when did that happen? When? When implies time. After how many seconds did that happen? Well, that's the x coordinate or the t coordinate, depending on how you want to look at it, 3 seconds. Okay, so it reached the height of 55 units at 3 seconds, and we know it's seconds because it says that here. Okay, so anyway, that's how you do it. Hopefully that makes sense. And for my student watching, good luck, and I will talk to you later. Take it easy.